Okay, so welcome to the lecture number 8. It's 8, or it's in the middle. So we moved past beyond the introduction, so there is no reason to recap. So basically, I believe I made my case for why evolution operators. So now let's finally get to how evolution operators. Okay, so we're moving past the chapter 1. We're not chapter 2. Only 7 weeks. So evolution operator. So big step forward. Yeah, so let's talk about how evolution operators. And we will begin with a section 2.1, this convergent series. Small, unassuming title here. So in the basic form of the evolution operator, as we encountered it in one of the first lectures, is like this evolution operator. It's defined based on the series expansion of the exponential function, right? So we have this exp normal function, exp number function, right? And we know, I hope everyone knows that there is this Taylor expansion of this function. Press some buttons, okay? Let me write it like this: n to infinity, and there is a sum, partial sum, from 1 to n, z k over k factorial, which is conveniently, it's often written like in one symbol. This limit is written in one symbol. You just say, okay, I sum to infinity. Right, so this is a exp function for complex value arguments, a very nice and robust function, and we took this definition basically and now replaced the numbers with operators and said, okay, this will be our evolution operator. So we moved from this to evolution operator. Evolution op. We can add that it's generated by Hamiltonian H, in the sense that this U, so in superscript to remind us what the generator is, T, function of time, and we said this is E to ITH, so which basically means that we have to replace we are replacing the number, the argument z, with operators. 1 to n, I, t, k over k factorial, and h to power k, which again, from time to time, when it's convenient, we'll just use this shorthand notation with infinity here. HK. So this means that our evolution operator is a limit, is a certain limit of like a partial sum of operators of this form, okay? Or its value is the value to which this series converges to, okay? So for the sake of evolution operator itself and any future series that we will encounter, I will encounter quite a lot of them because we will be constructing some perturbation theories. I decided that it will be prudent to talk about convergence of series, okay? Because it is most likely you have been taught about convergence, series, and stuff like that in some maths course or something, but it was a long time ago, right? And nobody remembers that. I mean, especially when they taught it to you, it was like without a real context. It was just some theorems and whatever, some problems to solve. Some were tricky, some were too difficult to understand, some were easy. So it's like nobody remembers this stuff. Okay, so now we have a good context, you know. So it's maybe good to refresh all this stuff, the modes of convergence. Okay, because as it turns out, this is kind of key topic to understand not only what this operator here actually represents, but also, you know, when we get to, we will generate some perturbation series, some perturbation theories. It will be the convergence will be a very important question to ask and to answer, because it would you know, does it make sense? Well, if it converges, probably it does. If it doesn't, maybe there are some problems. So we have to know what we are doing here. So this will be kind of mathy, not interlude. This is like a main topic, but we'll be talking about actual convergence. So let's begin with the basics. So the most rudimentary definition of converging series is formally represented by the following statement. So first formal, then I will convert it into words. Convergent series, formal definition. So the thing that I wrote here, so a guy like this, UK, I will explain my notation convention in sec, which is the same as taking a limit of a partial sum. K1, U, K, which is another alias for this would be n goes to infinity. The partial time I will sometimes denote it with capital letter, okay? And the limit, the value, so that would be the value of the limit, okay? So I'm packing in all the possible variations of notation. So we will have a terms of the series, which will be a small letter, usually. I mean, I will be thinking about operator value series because, you know, operator value series is what we are about. This index here enumerates which term in the series we are dealing with, of course. So capital U would then mean a partial sum. So, you know, the thing written here. And if I take a limit, this is a cute way to denote that this is the limit. And the formal definition of this guy would be written in terms of quantifiers. So hopefully you saw stuff like this for all epsilon greater than 0. There exists an epsilon such that for all n greater than an epsilon, the difference between kn u k minus is less than epsilon. Have you seen stuff like that? Quantifiers? For all epsilon, there exists. And yeah, so I don't know, man.
Long time ago. 16 years old.
Yeah.
Now I'm more 12 years older.
Yeah. Yeah, so this is like weird symbols, but hopefully you are familiar with this. In words, what it means, so I have here a nicely written definition. So the series U of terms U is convergent to a finite value, this U with infinity here, when for any accuracy goal, that would be epsilon, okay? It is possible to find a threshold number of terms. This would be this n of epsilon, depending on epsilon, such that any partial sum of more than this threshold number terms, so thing like this, approximate this infinity value with an error smaller than epsilon, okay? So basically, a convergent series is defined in terms of a approximation procedure, okay? So this symbol here, it represents a procedure, okay? All right. Yeah.
It's maybe a little bit of a nasty question, but how this definition is useful? Because usually we have a problem in mathematics that we have a definition that is concise and it's very well defined, but then if you want to prove a convergence of something using this definition, it's actually impossible. Will this one be useful?
Excellent comment. Very nice. I won't have to make it myself. Thank you.
I couldn't let you.
No. Very nice. Good eye. Because what you are saying is like, if I want to check for convergence, so look if I pick my accuracy goal, my epsilon, can I find this threshold so that the error will be smaller? So let's say I have the terms are given, so I can calculate partial sums. Nice. But I am comparing this with this limiting value. But what is it?
I want to split because there isn't it like an implicit assumption that there exists a limit.
You start with if
yes.
Converges. So,
Yes. You could add here for there exists this U infinity value such that for every epsilon you could add it as a quantifier, but it's like
so you need to also prove the uniqueness and existence, right, for the U infinity.
Well, that it's
then you can actually start talking about finding it.
This is a good definition. Okay, there is. Of course, you would have to like go through the like all the proofs. So uniqueness is very important here, that it is actually sensible and stuff like that. But we won't go through all those details because that would be just a masturbation of some kind. If you want, there are a lot of textbooks, and you can pick one you like because there are a lot of ways to prove this stuff.
The reason why I wanted to along the lines that he was asking, because the existence is required, right? So does it follow from the definition? I think you need to prove that whether this limit exists or not, right? Only then you can say that the series converges.
No.
This is the definition specific. In this way, it is specifically the definition of series convergent to U infinity.
Yes, to the value. Yeah, to the concrete value.
If you add this another quantificator, it would be the definition of series convergent at all.
I mean, if this value to which you converge, which you test for error, would depend, for example, on epsilon, that would be a bad definition. That would be some kind of definition, but it would be bad definition, not what we mean here. Okay.
I think the existence and all relies on that limit. So I guess the proof will come down to the question of whether that limit exists or not.
Look, if this guy is not here, this will all fall apart, right? If this does not exist, I mean, it is a robust, mathematically speaking, formal speaking, it's a good definition, although it is kind of useless because you would have to know what this U is to check if it's convergent, but to know this guy, you would have to converge the series, which is like, non-constructive.
Shouldn't there be like there exists U infinity such a probability of psi?
You could very well, very much add here that there exists such U.
This is for every.
Oh, sorry. Sure. Exists such U infinity. You probably, you would have to say that it's actually finite. Right?
Actually, I would say that if it wasn't finite, then the part-to-variate would never be satisfied.
Yeah, and then you have divergent series. If the series is infinite, you cannot satisfy it. It means that the series diverges.
So even without this, with the fact that this is finite, it would still be a proper definition.
Yeah, but if you want to be more specific, you can add this. It's because depending on what nomenclature you want to use, sometimes people tend to say that instead of saying that the series is divergent, they say it converges to infinity. It's a semantic stuff. Sometimes it might be useful to think like that, because there is also a possibility that the limit does not exist. So this would be the case when this U is not uniquely, there's no one.
Let's say there exists a unique U.
Yeah, but the limit definition always.
Yeah, you already had, right? There is this concrete value.
The limit to exist.
Yeah, because if you imagine oscillatory function, like sine or cosine or whatever, right? It does not. The series the Taylor series for sine and cosine converges, okay? But the convergence of you can think of partial sums as a sequence, okay? This is not different from the limit of the sequence, right? Each term in your sequence is a partial sum of your series. This is basically how it is constructed. So you know that, let's say, sine or cosine, the limit in infinity, for example, does not exist, right? Because there is no one value, because it's always between -1 and 1. So if you encounter such a thing, then you don't have a convergence, right? Limit does not exist, but you also don't have divergence, because it's not blowing up to infinity, right? There is a third option. That's a new one. I see you guys. You really want to dig into the nuances.
It's the divergence. The tożsamy. Equivalent to convergence to infinity or minus infinity. I feel like
this is semantic. If you choose to call it like that, then yes.
X times sine x wouldn't be divergent, but still not have, because it blows up to infinity, but it actually neither plays in plus infinity nor in minus infinity. I think it would be divergent, but it wouldn't be convergent to infinity.
This, yeah. I mean, if it you look, mathematics, you can, if you have a purpose behind choices of definitions and words, it's very much allowed and a good practice to go for it. If you want to make a distinction, because there is a reason, you can go for it. So you can make. But here, we are mostly interested in converging series, okay? Because evolution operator is good to be convergent. Yeah.
What is the norm of the operator?
So Hubert interrupted me when I was going to the second stage, because this is how we measure the error, right? Because it is an approximation procedure, right? We want this this difference to be smaller than the predetermined accuracy goal. So the question is, how do you measure the error, the deviation? And the answer is you have to pick a norm, right? The function that takes elements and assigns magnitude to them. So which norm you pick depends on what kind of series you are dealing with, right? So if this was a series of number valued terms, then you would, so if number valued series ES, it looks all the same to me, then the norm would simply be an absolute value. That would be a good norm. For complex numbers, for real numbers, is very good. And it is an absolute value is a norm, okay? Because norm has to satisfy a couple of things. We'll talk about it a little bit later. If you have like a ket or vector valued series, which is, why not? It's very much possible. Then your norm for a ket, or something like this. Well, a canonical norm would be nice. For example, you could use just bracket. Although don't forget about square root to get a proper norm, okay? And in the event of operator value norms, what norm do you use for operators? This is a very good question, very important to answer, but let's leave it for later. We don't need to know for now. We just have to know that we have a norm. So triangle inequality is satisfied, for example. It's a positive number, 0 only for 0. So for 0 operator, 0 vector, 0 number, etc., etc.
Just maybe the only question that may be relevant. Can it happen that in terms of some norm the series is convergent, in terms of another norm it's not?
Very nice. There is an answer for that. There is a theorem about equivalence of norms, but let's leave it for later. This is excellent. Yeah, this is like crucial question, right? And as a matter of fact, there are scenarios. Okay, so let's spoil a little bit. There are scenarios where norms are equivalent in a certain sense. There is a certain sense, and then it doesn't matter. Really doesn't matter. But it's not always guaranteed. Okay, not all spaces can be equipped with norms that are equivalent and stuff like that. So there is if you go into very maybe not pathological, but difficult spaces. You have to work with difficult spaces. It actually, you would have to specify convergent in a norm, blah, 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 okay? Sometimes it's important. It's a, with measure, if you're doing measure theories, this is often important to specify. I mean, sometimes you have to say it, not always. For finite dimensional Hilbert spaces, so we are dealing with operators, finite dimensional matrices, you don't have to, norms will be equivalent, it's all fine. So we won't have to worry about this.
So in general, there's no natural norm definition. Because we have a Hilbert space, usually you try to get everything from the inner product, so there is no induced operator norm.
Okay, with again, I don't want to talk about it right now. Yeah. There is with operators there are like two natural choices, let's say. So it's so that's why it's like this or this. I mean, which is more natural? And the conventional, there is a conventional choice, but it's equally natural as the other choice. I will talk about it later. It is important. I mean, then the norm stuff, there is whole norm foo, where people are specialists in norms, the relations between norms. Janek Kołodyński, our colleague from downstairs, he's probably could like talk your ear off about norms and different relations between them. Yeah. I mean, norms. When you get into it, you start to think about convergence in more.
We have to ask him to deliver a lecture, 15 hours lecture, entitled Norms.
No, I mean you could. You could. I'm sure you could. There are some crazy stuff you could like show, but that would be real masturbation.
You are not normal to speak this lecture. You will get normalized.
I mean, you will feel normal. If you join, all the people who are interested will join, you will feel normal for the first time in your life. Yeah.
If nobody is normal, then everybody is normal.
Exactly. Okay, so the norms, we kind of touch upon it, but before we fix the issues with this basic definition, I want to say a couple of words about that. So I call this defines this series, that this limit. I mean, this is essentially how all limits are defined. It's a procedure, approximation procedure. Okay, I want to explain myself what I mean by that, because this is kind of a nuance that maybe it's helpful to understand it. Because you think, okay, it's all this thing here, this sum to infinity. It's a number. It's this number, maybe, perhaps you would like to think, but this is not the case. Okay, it's rather this symbol. It represents a promise of this number. Essentially, it is a contract. Okay, so it's like essentially, in maybe simpler words, it's like you take this symbol and you use it in your formulas as if it was this value here. Okay, and you do all the manipulations as if it was this number here. Okay, and the manipulations can even include like treating this as an actual sum of terms. So maybe you do some manipulations per term in this stuff, but all those manipulations are not really manipulations of the number. It's rather you have a promise, you have this contract that at the end of all your formulas and manipulations, the promise is that any instance of this guy can be with arbitrary precision approximated by this value. Okay, so it's like it's a promise. You treat it as if it was a number, in the hope that at the end nothing broke down, and you can convert it into a real number, actual value, with arbitrary precision. You will choose. Okay, so it's like you will never really get this value. But you can say that with, you can approximate how well you want. And this kind of touches upon the, is any number really like actual value, or it's an approximation? And are real numbers actual like objects with a definite value, or they are just approximations because, how many decimal, after decimal points, So this is like, but with limits, it's good to have this in mind, right? That this is not like a value, but rather a thing that can be afterwards converted into a value. Okay, and this is not like some words, because depending on how robust this procedure, this convergence occurs, there is a tolerance on manipulations it can withstand. Okay, if your this convergence, this procedure is very particular about how you get there. You can imagine that there are only a couple of manipulations you can do before it all breaks down, and the promise will be broken, the contract will be broken. You will not get a value, approximated value at the end, okay? On the other hand, there are probably modes of convergence that are so robust that they can withstand whatever you do to them, right? And those are probably the best kind of series, the best kind of convergence, so that you can, there is really very little difference in treating them, making the distinction between a value and the procedure, right? And basically, so you have very fragile convergence. There are series that are very fragile, which is like basically you look at them funny and they explode immediately. And there are modes of convergence like exp function, for example, which is like the most robust way. You can do whatever you want to this series, okay? The contract will be always fulfilled. It will always behave as you expect. So the manipulations it can do, come at me, bro. I can do it. So there is a distinction between kind of convergences, okay? So the limit is not really a number, it's a promise that you can convert into a number with some arbitrary precision. However, depending on how this procedure actually goes, it may be fragile or it might be robust, okay? So this is like a thing to think about a bit and be cautious. I mean, this is basically also the explanation why we, we have a definition of convergence, let's just move on. Because now we will specify modes of convergence because of having this in mind, back of our heads, that some modes will be fragile, some will be robust. So we have to check which one is which one we want, okay? And let's say evolution operator, how does it converge? Robustly or fragilely? Okay, if it's fragilely convergent, it's probably not worth building our theory around it. Right? Okay, so I said this. So before we go to break, because probably I was laboring under this assumption that this will be just breeze through all this stuff, but of course, there were cool questions, so everything is slowed down, but it's fine. So as Hubert noticed, this is kind of unconstructive, right? Because we have to know this value to check if this converges, so that you can get this value, right? It's like. So it is not very constructive, but it is a good basis to go from this. So the first upgrade to this definition, let's move to the new page maybe, because I don't want to interrupt with a page shift. So the first upgrade would be something. Maybe you recall Cauchy convergence criterion. So famous name Cauchy, right? It's all over calculus and mathematics, Cauchy convergence criterion. And let's see if you will have questions. Okay, and it's the Cauchy convergence criteria basically says that the series converges in the sense of this basic definition if and only if and only if. And there is a formal, again, quantifiers and all of the stuff. So for all epsilons, so for any picked accuracy goal, there exists a threshold number of terms, n epsilon, which depends on the accuracy goal in general, such that for all n greater equal to m that is greater than n epsilon, so we have threshold and we have two indices, such that the difference between a partial sum of n terms and the partial sum of m terms which is nothing but a norm of this kind of sum that goes from m plus 1 to n. So there is like you pick a couple of higher order terms, that this is smaller than epsilon. Okay? So you see, there is no value of the limit. So instead, what we are saying, what this theorem says, because it is equivalent to this first definition, it's like the convergent series are such that the accumulation of any number of terms of high enough order, this accumulation is arbitrarily small. Okay, so you can sum up tails of your series, and this, the sum is, you can make it arbitrarily small if you go far enough into your series. Okay.
So that means up to a certain term that will be the major chunk of your
Yeah.
You can neglect the after a certain point.
Exactly. So this is like so basically it tells you that you pick your accuracy goal, and this basically tells you that there is like there is certain number of terms you have to take. Yeah, exactly, which gives you the value of this accuracy, and the rest is basically negligible. Okay, which is nice. Okay, which is this is the power of this is obviously the power of this Cauchy's criterion is that you don't have to know in advance where we converge.
At least you can check if something converges with this one, because previous definition was hopeless completely.
Yes, was hopeless.
This one here you can check, but yet you cannot get this part value to which it converges. So
but
proof it exists.
No, but it's like Sarah said. There is a number. I mean, of course, what is this threshold number? You would have to like check, right? But you know that you just have to sum up couple of terms to know that okay, this is the bulk of my stuff, right? And the rest is I can just neglect it.
But like you said, this one helps you to find something compared to the last one. We had no idea of knowing anything. And we have some number up to some epsilon we can find.
Let's
working definition.
And the interesting thing about this, because it tells us, I mean, you can take any number of terms in this tail. If you pick, you just take one term, so which means you take n equal to m plus 1. Okay, so if you pick n equals m plus 1, then you will get that n norm is less than epsilon. In particular, you add more, it will be still less than epsilon, but if just one is also less than epsilon for any n greater than the threshold. Okay, which means that the terms of the series, for it to converge, that terms have to be like decaying. They have to decay as the index goes to infinity, right? So we discover here that the n u k going to 0 as k goes to infinity, this is a necessary condition. A necessary condition for series to converge. Okay? The terms have to go down to 0. Okay? If they don't, your series cannot converge, it will diverge instead. Okay? However, it is only in a necessary condition. It's not sufficient. Okay, there are examples where the terms go to 0, but actually they don't go fast enough to 0. So that because they are getting smaller, but you're adding more and more and more and more. And you can imagine there is like a sweet spot where they not going down fast enough so that they start to accumulate.
Like 1 over n?
Exactly. The example is a harmonic series. Harmonic series. Like you said, 1 over n or 1 over k, because we are using k here, okay? Which is like 1 plus 1/2 plus 1/3 plus blah, blah, blah. Or it's k from 1 to infinity, 1 over k, harmonic series. And this guy turns out it blows up and it's divergent.
Do you remember what's the exponent threshold for convergence for working?
Converges, so it has to be something.
1 by n raised to p, that's what we're talking about.
I don't remember.
Like k to the 1?
It's between 1 and 2.
Yeah, but which is that?
I don't remember. The 2 converges some pi square or something.
Yes. It's it.
Or something like that. I don't
Pi
know.
square or 6?
Maybe something like that. I don't remember.
Just wondering.
I don't remember. Yeah, so it's evidently 1 over k goes to 0 as k goes to, but it's too slow. Okay, so this guy it's a counterexample to everything that is good in this universe. Okay, it's a bad series. Okay. Can I squeeze in one more guy before the break? Yeah, I will squeeze one more guy. So Cauchy is a useful stuff, very useful. We'll be using it basically all over the place, but it's not the only one. There are like 2 more tools, 2 more upgrades that we can use that are very, very important in this whole analysis. Or maybe let's go to break, because I want to go over the proof. Yeah, let's go to short break, okay? And then we move on to the next upgrade. So maybe 5 minutes, okay? Okay. Okay, guys. Let's move on. So we have our Cauchy. Basically, Cauchy replaces the first definition. That's what we. Although I'm surprised, I'm shocked, deeply shocked that nobody objected. Oh wait, is it equivalent? But if space has to be complete for it to be equivalent. Nobody mentioned it.
The criteria to be complete is that they have to
satisfy.
There is a.
That's the
Okay, so if you had minutiae, so it's like
always the spaces we are working with, always they are complete.
yeah, Hilbert spaces are complete.
Space, yeah.
Yeah.
That's the definition.
Even Banach is complete. every space.
Yeah. Because if it's not complete, because there is a possibility. If you have some space that's not complete, means that you might have you have your series or your sequence. It converges to something, but it actually this value to which it converges is ripped out of the space, just missing this point. So you converge, but there is no point in your space because you define like that. So it's basically you put it back and you have a complete space. So in that case, if there is no point to which you converge in your space, you cannot say that your series is convergent because of formal pedantic stuff. And then, Cauchy criterion wouldn't, it would claim that you are converging, but there is a caveat here.
Yeah, but again, that definition only requires vectors to be every Cauchy sequence of vectors to be convergent, not operators. Right?
I mean, operators.
For space, it only requires convergence of vectors.
You can make vector space of operators, no problem. We are working complete. It's equivalent for us. Okay, we don't have to worry about that. But it's I was surprised nobody attacked me for that. Okay. So that was Cauchy's replaces, but it's not the only tool in our toolbox. The next thing is so-called comparison test. Next upgrade. It's a side grade. Okay. Next side grade. Side grade. It's not upgrade. It's another thing. Okay. It's you put it into your deck.
It's the first side.
Yeah. Comparison. We won't be. I don't think we will be forced to go for downgrades. Comparison test. Comparison test goes as follows. So let me just write it verbatim. If a convergent series of non-negative terms, negative terms, and let me write down this series. So we have here series that goes k to infinity w k. So it converges. So there is some value w infinity, which is finite, and non-negative. So each term is it's a number that's greater, not negative. So if a convergent series of non-negative terms w dominates, I like this wording, dominates, oh my God. Imagine it says dominates, probably doesn't. The tested series. The tested series. That is, there is a index threshold n0 such that for all k beyond this threshold value, the norm of our tested series, which would be u, is smaller than terms of w. Okay, so it's not like the whole series w has to be greater than our tested series. It's enough that at some point it starts to and they call it dominates, which is cool. So it dominates. So if a convergent series of non-negative terms dominates a tested series, then the tested series converges. Then UK converges. Converges. Okay? So rather than looking at the series itself, you look at different series a simpler series because a number series. And from convergence of this other series, you can conclude that our series converges also. And it is instructive, actually. Sometimes it is instructive to check out the proof. Why is it so?
In Polish it had a funny name. Stwierdzenie o dwóch ciągach.
O dwóch ciągach?
Coś takiego.
Jest o trzech ciągach.
O trzech ciągach, ale o dwóch też było właśnie przy nieskończoności.
To też możesz w kanapki brać.
No, wtedy
Od dołu, od góry.
biegał do...
To o dwóch ciągach wynika chyba z tego, że to jest negatyw. To wtedy ten trzeci ciąg jest z założenia wzięty
Okay, you're Lechi stunning too much. Let's do the proof. The proof.
Legislation. Legislation.
So let me. Proofs are cool, but I have to be careful not to make a mistake here.
As long as they're correct.
Yeah, I mean, some proofs are good to see because they actually reveal. Okay, so in general, there are two kinds of proofs in mathematics. There are constructive proofs and the proofs of existence, basically. So you can either, you have some theorem, the thing is such and such, blah, blah, blah. And the proof is you actually construct the thing so that it has the properties the theorem states. Those are the best because they basically tell you how to get the answer, right? So the proof themselves then have a lot of value because the theorem is just a summary of the proof. Okay, useful stuff. You have proof of existence, that something exists, but it's not constructed. It's whatever, man. It's like formally okay, you've proven something, but it's like, did you really? No, this is like they are not very good. Okay, so we love constructive proofs, and we are haters against those other existence. And there are usually there are some funny stories around those kind of guys, like a axiom of choice story. It's like, we don't like those. So this is a constructive proof, actually. So let's start by let's pick an accuracy goal. Goal. So that means epsilon, right? We pick some epsilon. Then I don't know how much to write and how much to say. So I will be like I don't know. I will do both, I guess. Then since the W, the dominator, is convergent, right? So we pick accuracy goal, which means because it's convergent, then this means that there is a threshold, the threshold value, the threshold number of terms. Since WK converges, there exists an epsilon, which can be, we can actually select it that it's an epsilon that is bigger than n0, this n0, okay? Any objections? Is it am I stretching something? Okay.
This n0 is kind of arbitrary. Just to hold this.
No, it's not arbitrary. There exists such that beyond it, okay, it's not unique.
Okay.
Right? Because if you pick an n0 plus 1, it's also a good threshold value, right? An epsilon is also like that, because it's like you pick a threshold and you say, okay, there is an epsilon the threshold, such that when you go beyond it, the error is less than epsilon. But you can say, okay, I go any number of times beyond the threshold, but so I can like say, let me pick a new threshold that is k plus the first threshold, and it's also fine, right? Because it only matters what happens when I go beyond. So I can pick there is some minimal n epsilon for given epsilon, and I can always shift it so that it's bigger than 0. It exists. Okay, there exist thresholds, and also and n greater or equal m greater n epsilon. This is from Cauchy, such that the norm of m plus 1 to n wk. So this is we are using Cauchy criterion now, basically invoking Cauchy criterion, because w's are number series. So the norm is just absolute value. M plus 1n wk. And moreover, it is non-negative terms. So this absolute value does nothing. Okay? So this is actually equal to k m plus 1 n wk. And from Cauchy, this is smaller. All this is smaller than epsilon. Okay? Right? We pick an accuracy goal. It's convergent. So we pick a threshold and pick 2 indices beyond the threshold. And we know that when we sum those terms, they will be smaller than the accuracy goal. The accumulation will be smaller than accuracy goal.
Why are we taking them to be positive real numbers?
I mean, if we didn't, we wouldn't get the theorem. Series of non-negative terms.
Okay. Well, so this doesn't work for anything other than numbers. Well, it says non-negative terms, non-negative numbers.
I mean, can you have a non-negative vector?
For example, positive matrices.
So I would say positive semi-definite.
Positive maps.
I'm saying non-negative means it has to be number because it makes sense.
I'm just asking.
Okay, are you just asking? No, good.
Given that we can construct some comparison between the elements and assigning one to be
No, it's fair. It's fair.
No, but is there not like, does this only work for non-negative numbers?
No.
For example, wk greater than or equal to 0. So you would have to define what you mean by that.
Positive.
Now you are actually giving more structure to your terms.
That's why I'm asking. Yeah. I mean, we are assuming if we have numbers, we are still are assuming some kind of structure. Perhaps more basic than just whatever structure might be within matrices or whatever. But
So that's why I'm going over the proof to show you why these choices had to be made or are convenient to be made. Okay. So this is what this estimation. This is what we get from the fact that it converges. The W converges, and the norm simplifies. It no longer plays any role here because we picked them to be positive, non-negative numbers, right? That's why we did it. And then, so now we can use the domination. Now we use domination. So we combine this estimation for W with a triangle inequality for our tested operator value, let's say, series. So we take like a piece that would come in if we try to do Cauchy stuff, right, of UKs, and the norm. So this is the, if we want to satisfy Cauchy criteria, this would have to be smaller than epsilon, right?
Yeah, just a comment on that structure, because it seems that in a way the WK doesn't depend because you just need some numbers. So how you get that WK numbers doesn't matter for this proof, right? So in a way, like
I mean, if you have a dominating
whatever
series,
fancy thing you're doing, you end up with some numbers to apply this.
yeah, I mean, let's carry on. We'll explain this stuff. So now we can just use, say, every norm has to, whatever this norm is, it's operator norm, we didn't define it yet, but every norm has to satisfy triangle inequality, which means that we can go under the sign of sum with a norm, but there's a price to be paid, but this is a good price because it gives us estimation from above, the bounding stuff. So we have sum of k m plus 1 and the norms of our terms, okay? And now we come in with domination. You know, the W dominates this. Tak. Right, so we can, you know, we are n is n m are beyond the n0 threshold, beyond the domination threshold. Right? We can always pick this like that. So this, we have another estimate here, m plus 1 n, but this time with w's, not l's, w's, okay? And this guy from here, this is smaller than epsilon. Therefore, our series satisfies Cauchy criteria, right? Okay. So this is the proof. This is the proof. As most stuff, you have to just, you know, bound something. You find bounds for some stuff. Like most of mathematics is looking for bounds. Okay, you are bounding this with that, and then everything else works out somehow, hopefully for the best. But there are a couple of insights that we can draw from this. Oh, wait, I did a proof, so I can do the thing.
Yes.
I can do the thing. So couple of observations. One, given if someone gives you a series, operator value series, vector value, whatever kind of series, just by looking at this, we can notice that you can always construct a dominating series for your original series, right? You just take series of norms of your terms, right? Like this stuff. You know, this is a norms of our original terms, gives us a terms, and they are automatically dominating our series. So that's one, okay? And the other thing is that this whole exercise shows us that even if we have some crazy series of operator value terms, vector value terms, or distribution value, whatever, some crazy stuff, this comparison test basically tells us that whatever crazy space you are working with, the convergence of your series is actually determined by the convergence of some number series in the end, right? Because it's like you just dominate, and you can, for example, dominate with norms. This is numbers, and the convergence, if this converges, whatever dominates converges, you have your convergence, right? So you don't have to worry about what it means to, you know, error for operators. No. You can boil down everything to looking at some number value series, which is a huge relief. Okay, without that, we would be, you know, it would be very difficult most of the time. If you are forced to some other means, not this kind of comparison testing, then it's like, I don't know.
So the whole logic is you first write out all the convergence rules for numbers, and then whatever fancy mathematical structure you construct, you define some function which converts into a number, and then use the result you have
Yes,
to prove it. Okay.
yes. This is how. If you are a mathematician, this is how you don't work hard. You work smart. You don't want, you don't want to fight with this beast. You want to have advantages. So you just convert everything to simple case. And so this is how we do. So how we do it. That's why those, like comparison, the test criteria that like will use some bounds are so powerful because they basically rely on this converting complicated objects into simple numbers. Non-negative numbers are even better than negative numbers or with indeterminate sign. Real numbers are better than complex numbers usually, and so on and so forth, right? So this is like the setup for doing that. And the fact that the dominating series is like always there. You have to have norm to talk about convergence anyway. So we have just one step of obtaining a dominating series. And as a matter of fact, if convergence of your tested series is actually determined by convergence of series of norms, because here we have W converges, right? We don't know if this converges. I mean, we know it converges because it's dominated by W, so the series of norms also converges. So there is this is so important when the convergence is due to comparison test with a series of your norms. Okay, so important that it actually has a name. It's an absolute convergence. And series convergence converges because of the comparison test with a series of its norms. Then we say that it converges absolutely. Okay, and this is like the most basic mode of convergence. If yeah.
Counter example, like you're not a convergent absolute.
Yeah, because as you can imagine, so we are happy when we are looking for this. Okay, we are looking for series that converge absolutely. However, this does not mean that all series converge absolutely. There are examples of series that converge even though the series of its norms does not converge. Okay. Example is actually you take an altering series. 1 minus 1/2 plus 1/3 minus 1/4 and so on, which is basically minus 1 k plus 1 divided by k. And this guy converges, and the value is, I think, logarithm of 2. It converges. However, if you take a series of its norms, what do you get? You get harmonic series, which diverges. Okay? So there is an example. So if a series is such that it's not absolutely convergent, we call it that it's conditionally convergent. And they are really crazy. They're very, very weird. Because as it turns out, if you have a conditionally convergent series, there is a theorem by Riemann that states that just by taking this series, conditionally convergent series, non-absolutely convergent series, and just by rearranging the order in which you are summing the terms, you can get any value, including plus minus infinity. Anything, you can get anything. So it's like the most crazy. So this is like when I was talking about when the procedure is like very peculiar about the way it's carried out. This is what I mean. I mean, you have to be if you do any disruption to the way you are, summing those terms, you just get completely different results, including plus minus infinity. It's kind of crazy, right?
So is this where the name conditionally convergent comes from? That it's conditioned on the order, or what?
Yeah, I mean, I believe this is it. That because it converges to some value, but under the condition that you sum it up in the very specific order. Any permutation will blow it up, and something else we will obtain something else. So, and as a flip side, you have absolutely convergent series. Okay, not you can do whatever you want. I mean, it doesn't matter. It's actually because if you are talking about sequences or series, there is a definite order in terms, right? And we are referring to it, right? There is a threshold index, and beyond this index, the things has to be smaller, and so on and so forth. So there is a definite order, right? And this matters, as it turns out, this matters for those conditionally convergent series. But for absolutely convergent series, you can scramble this order, and the result will always be the same. I mean, it will always converge to the same value. So there is a concept where you have like a sequence where instead of a tuple where the order is definite, you have just unordered tuples, let's say. I forget how they call it, but there is like a sequence without an order. There is a name for that. I don't remember what the name is, but it's actually...
Set cannot have doubles, but
Yeah. So it's not a set. It's not even the list. It's like something without the structure, and it's so it's so robust. Absolute convergence is so robust that it actually the order doesn't matter, which is kind of
Is it the strongest type of convergence?
Sorry?
Is it the strongest type of convergence?
For like
Absolute.
at the moment, yes.
how do you define strength of convergence?
Basically, how robust it is against manipulations. Okay. So, for example, I was saving it for later. But for example, because you have a series A, you have a series B, let's say, right? And now, let's say you want to multiply them. Okay, you will get some. If you decide to multiply it like term by term or some, I mean, some procedure for multiplying those sums, partial sums, you get some new series, right? And but there is no, I mean, will it converge, for example, or will it behave as if in the way that actually I imagine how I imagine the multiplication should work? And the theorem is that if at least one of those series is absolutely convergent, the product is also convergent.
Absolutely, or just convergent?
I don't remember exactly.
So that's bit weird. I would expect both of them to be.
I think then it's absolutely. If at least one is absolutely convergent, then I think the product is.
And the other is convergent.
So it's like it's an important ingredient. Okay, the absolute convergence allows you to do, for example, that.
Is it if and only?
No. Because conditionally convergent series. If you are, the procedure is particular, you get something, maybe not crazy. So it's like the coincidences. Everything might be such a coincidence that it actually works just fine. But if you want to have guarantees that nothing blows up in your face when you start manipulating, absolute convergence is a must, basically.
So you can take a convergent series and decompose that as you wish.
Exactly. Exactly. Sub-series, you can take sub-series. It will be convergent absolutely as well.
And each of them will each of that decomposition be guaranteed to be always absolutely convergent?
Yes. It follows. With conditionally, not.
Yeah.
exactly.
Can be okay. Okay, yeah, I see.
Actually, this is like the Riemann theorem, the one where you rearrange and get any value. It relies on the fact that you can like pick a sub-series, and you can like the positive value, negative values, and you can like see. All this construction works only because the absolute it's not absolutely convergent. Because if it is absolutely everything, every like sub-series, every piece of it is just nice, robust, everything was just fine. The convergence, the mode of convergence is basically that, it's Cauchy criterion. There is like a bulk of terms. When you sum them up, whatever order you want, this is like a value, gives you the value. The tails is just a small correction, okay? But if you have something like this altering series, you can see that it's like it tries to blow up, but you are like countering with plus terms, positive terms will try to blow up, but you are countering them at each step with negative. It's like very, very balancing on the edge, basically, right? If you just move a little bit, it starts blowing up.
So infinity minus infinity is log too.
Yeah, the Riemann theorem is basically you are manipulating infinity minus infinity, but in a special order, so that it's actually any value can be obtained. Your absolute convergence is like you cannot do that because of those terms. Each individual term is well behaved. Yeah.
Do we have something like even divergence too, like absolute divergence? Because you can make the infinite divergence to a convergence. This such research with Ramanujan summation. It is infinite, but after non-renormalization, it can be convergent.
A conditionally convergent series, you can make it divergent by rearranging terms. So is this like a clue to the answer to your question?
No. Imagine we have it like 1/k.
Yeah.
If you want to normalize it, this would be conditional convergent because it would be convergent if you want.
Yeah.
Depends what you mean by
No, wait.
multiplying the terms by something, then it's simply changing the series.
Changing the series.
Yeah, you are changing the series.
No more what you had.
That's if you have series that depends on parameter.
That's something like
That's a function.
Yeah. Exactly.
The series becomes a function, which actually. Oh no, we have one more test. Let me take time for it first because I don't know if. Because we are okay, so it's like
Half an hour.
to kind of. Oh my god, I wanted to make another proof. I can leave it for later. So the absolute convergence, if your series is just you have terms that are just some fixed values. I believe saying that absolute convergence is like the GOAT. The top-notch type of convergence that can be. I think that's kind of true. However, we will our evolution operator is not like that because it also depends on time. So it's a series of terms that parametrically depend on an argument on time. It's a series not of like value, not a value series, but a function series. Okay, terms are functions, right? So this gives you absolute convergence is only like a first step. Okay, it's important, but now you have to combine it with a series that are actually functions of some parameters. And then it's like you have to expand what is meant by absolute convergence. But before we get to uniform convergence, because this is where we are getting with that, there is one more crucial test. So we have comparison tests which showed us the way, the absolute convergence way. but there is another test that is like very practical, and it also leads to kind of cool insights.
This upgrade or side grade?
It is a side grade. It is a side grade. It's just another skill slot. You feel you have more tools. Another side grade. Another side. Right. It's not Diablo 2. You have more than, not only left click and right click. You have more skills on your skill bar. So this guy is D'Alembert's ratio test. This I managed to find the name to attach to it. The D'Alembert's ratio test. Ratio test. So it goes like this. So first you compute the following ratio. Compute the following ratio. So this ratio I will reserve small r. Okay, there will be a big R as well later. It is lim k to infinity, and ratio, you take a norm of u k plus 1 and divide it by a norm of u k. Okay, so you take two neighboring terms and you send it to infinity. Very cute, very, very cute. And there are three options. Then there are three options. Option number one, r is smaller than 1. Okay, in this case, UK converges. I mean the series K converges absolutely. Okay, this is good. When this is less than 1, we are happy. We are good to go. Second option, are greater than 1. The series diverges. Bad news. Okay. And now hopium, r equals 1, inconclusive.
For r smaller than 1, there's also the harmonic series, which diverges.
For harmonic series is, I think it's 1, ratio is 1? No.
Is it?
Yeah, because it's like k plus 1 over k.
It's infinite over infinite.
It's k over k essentially, so it's 1. So you are in the inconclusive. Inconclusive means that it can converge, it can diverge, or the limit might not exist. Yeah. It's like you nothing can. So it's a hope. It's a hopium. You're a huffing hopium because maybe it's still fine. It might be fine, yeah. But this is the best, right? And the proof is again kind of cool because it involves geometric series, which we all know how to calculate. And I don't know if they want to go over it.
Yes.
Okay, let me go over it because it is kind of, there's some value in seeing how it works actually, because it is also a constructive proof, which we like, and it illustrates the power of estimating stuff. Just you bind something from above, and then you are quite happy. So the proof we will only consider the first option are less than 1. The others are, I mean, the third one is the least interesting. It's like, oh, I don't know what, I have nothing here. That's the basic. The proof is I have nothing. I don't know.
We prove that we do not know anything.
Exactly. So assume
No.
R is less than 1. Okay. So if R is less than 1, this means that you can always squeeze something in between R and 1 and still get something that's less than 1. Okay? So then there exists epsilon greater than 0, although probably very, very small. Such that R plus epsilon, which we will call tau, okay? R plus epsilon will be tau, which is still less than 1, okay? So we give ourselves a little bit of space for our ratio. And then, so exists epsilon, but also there is such n. No, there is n. There is n such that okay, I have to move here, such that the k plus 1 divided by uk, that this is smaller than tau for any k greater than n. Which is basically, that we are translating this ratio into some finite numbers, okay? And in particular, if this is the case, in particular, we can do the following. So the n is the threshold value, okay? So we can say un plus 1, then the norm is smaller than tau times un, right? It's just a ratio. This, right? Mm-hmm. And un plus 2, probably already know what's going on here. This will be smaller than tau times un plus 1, which is smaller than tau square un, right? You see what's going on here? This tau will come in. So you can do it plus m will be smaller than tau m. The point is that we are estimating our terms with un, which is universal for all of them, and the powers of tau. That's why geometric series comes in. But it also means that a series constructed with terms wk equal to, how did I define it? 1 over tau n un tau k, which is non-negative, right? So we have a series of non-negative numbers that dominates our series u, okay? Because from this we have series w dominates u k, because a norm of u k is less than or equal wk equal to un by tau n, tau k. Okay? For k greater than n. Okay, so we constructed based on our ratio, thanks to the we have our ratio. From that we can construct a dominating series. So now the question is this dominating series convergent? If it converges, then that U also converges. And fortunately, this is smaller than 1. And this series, okay, 1 to infinity of wk, it's a we can pull out the constants, tau n, k from 1 to infinity, tau k, and tau is smaller than 1. This is geometric series, right? And from school, we know that this guy converges to 1 minus tau, right? That's why the ratio has to be smaller than 1, so that this geometric series converges. So dominating series, which is a geometric series, converges. Therefore, our series also converges, which explains why the ratio test works. Okay? So assignment, I have assignment for you to actually prove that geometric series converges to this value. Have you ever tried to doing that?
Nice. Yeah. More than 10 years.
Yeah, but with being like very,
11.
So the assignment 9, so like checking can I do this step? Are the things still convergent? Check out if you can be very pedantic about this proof. And it's also a good exercise to prove it again. So I have to finish this, and that's good because this is the place where I wanted to finish. So so we have a ratio test, we have comparison tests. They all basically work by estimating our crazy series with some number series, right? We want to have you take your crazy series, convert it into series of norms, basically, so we have number series, and now we want to estimate it with something that converges. If you can do this, you have an absolute convergence, and you are very happy, right? If this doesn't happen, you are in trouble, because maybe divergence, maybe conditional convergence, which is equally bad. Or maybe not equally bad, but also bad. And that's probably it for this week. Yeah. Next, we will move to recognize that we are dealing with functions, series of functions, operator functions.
Yes.
Yeah, this will be interesting. But we have our toolbox filled with nice side grades and upgrades, so we will manage. Okay. Okay. So thank you.